So now we've seen that in a modern IDE, like VS Code, there are tools available, like linters, which allow us to augment our programming abilities to avoid making mistakes or to notice mistakes when we create them. Right, so a linter is a separate program which reads the text of your code looking for obvious mistakes and underlines them in a word processor like underline squiggly. Beyond this, though, many IDEs, VS Code included, have support tools for advanced debugging techniques that will give you a certain special set of skills to find and eliminate those bugs. I don't know, do Liam Neeson references still work? How old is that movie? So returning to VS Code, let's take a look at these advanced debugging tools in practice, using our old friend rock, paper, scissors. So this is a modified version of the last version of rock, paper, scissors we saw. So it's written in procedural style. We have functions like get user input and game results and CPU throw, and then a main function which orchestrates the calling of all of those functions and manages the score for the user. But I've also accidentally, let's say, injected an error into this code somewhere. So let's try out our code and see if we can notice that there's something wrong. So we run our code, it asks us to play rock, paper, scissors. I will say rock, and I win. I will say paper, and I win. I'll say paper again, and I'm still winning. Notice the CPU's only thrown scissors so far. Oh, now it's thrown a rock, and then scissors, and then rock, 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 scissors, rock. Oh, it threw a paper. Okay. So there doesn't seem to be anything wrong with our random generator, although it does seem to be a bit less random today. And let's just make sure all these things work. So if we call paper and rock, so if I throw paper and the CPU throws rock, I win. If I throw paper and the CPU throws scissors, I win. So that's a mistake. If I throw paper and the CPU throws scissors, that should be an error. If I throw paper and the CPU throws paper, it's a tie. Paper and scissors, I win. Okay, so there's an error here. Paper and rock, I win. It doesn't seem like I can lose if I'm using paper. So let's see if we can't find out why. So returning back to our code here. So let's see VS Code's built-in debugging interface. So to access the debugging panel, it's down the left-hand side here. There's a run and debug option. Looks like a play button with a little beetle next to it. The first time you click it for any given project, you're likely to see an interface that looks like this. A big button says run and debug, and the option to create specific configurations if you need them. So we're just going to use the default options, so click run and debug. You're likely to get a pop-up window from the top here that asks which debugger do you want to use. You should already have the default Python debugger. It should be installed with VS Code's Python utilities. But if you want, you can find a different debugger and install that and use that instead. But we'll use the suggested one here, so click the first thing there. And you're likely to see a second pop-up window that looks like this one that asks, how do you want to run this debugger? Do we want to run it on a Python file with arguments? Do we want to run it as a whole module or some other options? If you don't know what any of these are, Django or Flask or Pyramid, don't bother using those options. Research them first and come back to them. Those are advanced ways of running Python files. Something you should understand is what a Python file is, or what a Python file with arguments are, although we haven't actually used command line arguments in our Python files yet. So we'll just use the first option here, which is debug the currently active Python file, which is what we're looking for. So click on that, and VS Code will take over. So a few things change here. Just to show all the changes here, some of them are a little bit hidden. So what happened was Python runs python.exe, but with its debugging launcher so that it's in this debugging mode. We can also see we have our prompt from our game saying which one of rock, paper, scissors do we want to use. Notice the left-hand side panel here has changed. Now we have a space for variables, a space called watch, and a space called call stack. We'll see what that looks like in just a moment as we walk through this code. And this little panel here pops up somewhere on your screen with all the buttons you need to interact with the debugging system. So these buttons let us step through the execution of our code. Now currently our code is paused because we have user input and that's where it got to. But if we don't have that user input paused, the code just runs as it normally would, and then it finishes. Generally speaking, there's no difference between running the code in regular mode or running it in debug mode, except that we now have more control over what we do with that. So let's run it again here. So we have these buttons at the top, which, going from left to right, the first one pauses the execution. So if our code's running along, we can click the pause button. That will stop it from taking the next step. So the next three are stepping options. So that's walking through our code step by step in different ways, where we can either step over function calls, step into function calls, or step out of function calls. There's a restart, which just restarts the whole debugging process, and stop, which obviously stops. So if I click pause here, and then have our code move past the user block, notice nothing else happens. The code is now paused, and these buttons in our window have all lit up. So now I can either continue, as say rerun the code from where it currently is, or I can start walking through with steps. So I can take a step here, and let's just do a step into. There we go. So we take a step and we can see where we are. So we just finished the user input. Now it's about to return the user. So I can click any of the step buttons will do the same thing here. And that goes back to where that function was called, getting the user input. Now we've stored the user. Notice down the left, it's tracking all of the active information in our code. A bit more space there. So it tells us all the local variables. Now that we're in this RPS function, it says the CPU, which is this variable here, has the value rock. We just returned from get user input, and that also got the value rock, because that's what I typed here. The score is currently 0, so that's another local variable that's being stored. We check the global variables. There aren't any real ones, although you can see the random module is in the global space. All of our function definitions are in the global space, and some of the special stuff that Python provides. But we don't need the globals for now. Watch section here I'll talk about in just a moment. The call stack, though, notice is, as a call stack would be, is just the stack of all the function calls. So if we're in the RPS, we have the module level, which is the global scope, if you will, and then our main function RPS, because that's where we currently are. And now if we step into, we've just finished user input. We'll have to wait till we get to another function call then. So the next step is check this if statement. That comes up false, so it skips. Notice it jumps down to the next line, prints out CPU throws. Hasn't printed yet, but when we click step, then it says CPU throws the rock. The next line says call game results, so if I go step into, we jump to the function game results. Notice our call stack now adds another frame on top of our main function, so RPS and then game results. Our local variables here are just the parameters that are passed in, so CPU is rock and user is rock. And then we take the first line of this function, it says if CPU is equal to user. That's true in this case, so if we step, we go into that if statement. The next line prints it's a tie, so we see it's a tie show up at the bottom. And the next line says return 0. So if I step, we'll return back out here, and score plus equals 0. So notice our score. So notice our game results return 0, and our score, if we go to the next line, hasn't changed because 0 plus 0 is 0. Let's show a few of the other buttons here. So let me just step to the next iteration of this loop. So we're at the top of our loop again. Now if we go to this function call, just to demonstrate what these other buttons do, so we could either step over or step out. Step out will run the code until we've left this function. So if we're in our main function, that'll pretty much end the game. But let's step over the get CPU throw. So that means execute all of that, but don't walk through it line by line. So as we go to the next line in the same function, we didn't walk through the lines inside the get CPU throw function. We didn't jump up to line 15, run through these steps, and then return back. The program still did that, but the debugger said, okay, well, we did all that, now we're here. Similarly, we can step into a function, and if we're like, okay, that function looks good to me, I don't need to walk through all the steps, I can then say step out, and that will run the code until we're out of that function. Now in this case, it hits an input statement, so it actually pauses the code for a different reason. I'll again say rock. And notice the code runs on its own, I didn't have to step anywhere, and we're back out of that function. One other important thing I'd like to show about this interface, let's stop our code here. So just looking at our regular code, we have this bug where when the user enters paper, it seems like they're always winning. So let's take a look closer at the game results to see if this function is doing the thing it's supposed to be doing. Now one way we can do this is to include what's known as a breakpoint. A breakpoint is an indicator for the debugger to execute code up until that line, and when you reach that line, then stop and walk through the step-by-step progression as we've seen it. So I'm just going to add a breakpoint to the first line in our game results. To do that, you just click in the margin, this little red dot appears, and that creates a breakpoint. If you mouse over, it should say, click to add breakpoint. Now when we run and debug our code, it asks us to enter our first step because our breakpoint is after that in the game results. So we'll enter our first step, and notice as soon as it gets to that line, we're given all the stepping commands and the code is paused. We can see the current values of all the local variables at that point, and we can debug from there. If we want, we can say, okay, that looks fine, scissors and rock, that doesn't really help us. We're looking for a situation where the user is always winning when they press paper. So let's press continue, that'll resume our code from this point on, which in this case loops around through one round. In this case, we won the game, that round at least. Our score went up to 1, and now it's asked us for our next entry, so I will say paper. And when I do that, the control of the code eventually reaches, again, this breakpoint line and pauses the code. Now we can see the CPU and the user both threw paper, so that's not useful to me. Let's try again to see. We want to get the CPU to throw scissors. So let's run again. Let's see if I get scissors on its own. It did. Now if that didn't happen, one thing you can do is actually change the values of these variables. So I could say this one was, for example, paper if I wanted, and then I could continue on from this line with the assumption that it's paper. So notice, because I changed it to paper, now these two are equal, and it goes into that if statement. So let's do another round here. Let's say paper again, CPU threw scissors for me again. So now let's test to see what happens in the situation where, in this case, the user should be losing, but we've seen in practice the user wins. So we'll step in. They're not the same, so that's good. This if statement should be false, so we've skipped it. And in this case, the win statement shouldn't be the case either, right? If the user's throwing paper, the CPU is throwing scissors, we're expecting it to lose, so this should be false, and we should go down to the else statement. But if we take a step, we can see for some reason this was true. So now what we could do is just manually look through this line and see why is this wrong, but let's go a little bit closer. Let's take all of these commands, I'm going to say copy, and we're going to add what are known as watch expressions. So you press the little plus button here to add a new watch expression, and this can be any expression you want. If you say 34, it's just going to watch that. The value 34 is just literally 34, so maybe not the most useful watch expression. A good reason to use a watch expression is to include complex combinations of values, like our if statement conditions here, to see what they're equaling. Now we have three sort of separate conditions that are all ORed together, so any one of those could be true to make the whole thing true. So let's check all three of them. So I'll put another one here, and I will take this text, and I'll do one more with this last one. Okay, a little bit bigger so we can see. So now these are expressions that are based on the values in our code. So the current value of CPU is scissors, and the current value of user is paper. So CPU equals scissors is true, and user equals rock is false. True and false gives us false. Looking at these three watch expressions, we can see that two of them are false and one of them is true, although we were expecting the entire statement to be false, so all three of them should be false. So let's look at the true one to see why it's true. We have CPU equals rock, which is false because CPU is scissors, or user equals paper, which is true. So false or true gives us true. Now this condition should be checking the pair of those two values. So CPU is rock at the same time that user is paper means rock and paper. So having an or here is a mistake. So we can change the value of this watch expression just by double-clicking on it and turn that to an and. We can see now that it becomes false, as we would expect. All three of these are false, and in that case it would have gone down to the you lose. So if the user throws paper and the CPU throws scissors, these are all false, and then we end up in the else branch. So clearly the problem is right here. In this statement here we have an or, where we should have an and. Save our code. We can restart the debugger. So it just kills the current process and starts a new one. I'll try again. I'll say paper, CPU throws paper, and our breakpoint is still there. It's important to remove the breakpoints once we're done debugging, but in this case we are still debugging. The CPU also threw paper, so let's change their value. So we'll go into the local variables and we'll say, instead of throwing paper, what happens if you threw scissors? Yeah, we step through these if statements. So again, we're expecting the first one to be false because they're not the same. We're expecting the second one to be false because this shouldn't be a win condition. The CPU is scissors and we're paper. The CPU should win. So we step, and sure enough, that came up false as well. We ended up on print you lose. So we can now step out of this function and return back to the main function where we've taken our result of a -1 and added it into our score variable. So the next step, our score becomes -1. And that's the debugging tool in a nutshell. So the IDE tools are quite useful, but I should note that you won't necessarily have them on the handwritten test in this course, or possibly even in your job interviews in the future. So it's a good idea to have an understanding of the low-tech debugging solutions as well as the high-tech ones. It's also a very good idea to avoid making mistakes in the first place. So good coding practices will help you avoid adding bugs to your code. The first step to this, as we've seen, is to design your programs. Expressing your algorithms in English is going to lead to fewer logic errors versus just sitting down and coding at a blank page. So make sure you plan your code before you actually write your code. You can plan this out in pseudocodes and flowcharts, as we've seen, or even just rough sketches on paper. Anything you can do that will take the ideas in your mind and turn them into something more algorithmically expressed will reduce the amount of assumptions that you make when turning those ideas into code later on. Also, as mentioned throughout this course, make sure you comment your code. Okay? Having organization in your code will make mistakes easier to spot, particularly in large or difficult to understand programs. Now, comments include function comments that tell the user what the inputs, outputs, and process of a given function are, but they also include line-by-line comments, not necessarily every single line, but sections of code that require additional description in addition to your function comments to explain why the function is doing what it's doing or how it's doing what it's doing in plain English can save a person from trying to figure out where an error came from in raw Python. And lastly, the key to avoiding bugs in general is to test your program. It's a good idea to write a little and then test a little rather than starting from the beginning, going to the very end of your code, and then testing the whole thing. Do the first little bit. Okay, I've got a user input. Let's make sure that's being addressed appropriately. All right, that's being addressed appropriately. Now let's attach a random generator. Okay, we got those two things. Now let's add a comparison. Test the comparison, make sure that's worked. And before we do anything else, let's make sure we have all of these pieces working independently, and then we'll try to connect them. It's also a good idea to use a wide array of types of inputs. So I don't want to just say lots of inputs, although lots of inputs can help. If, for example, you're summing a bunch of numbers from 1 to n, as in our previous example, the information you get from testing that code where n is 5 versus where n is 6, or if n is 7, or if n is 8, you're not getting much new information each time. However, testing that at spaces where n is 0, or a negative number, or a very, very large number, these will give you more information, testing the edge cases. So I don't want to just say use lots of inputs to test your code, although the more you test your code, the more likely you are to find errors that exist. But it's a good idea to try a wide range of inputs. So as to say, to test your edge cases, to test unexpected inputs, and all sorts of things that might conflict with the assumptions you made when writing your code. Now, two important kinds of testing are unit testing and regression testing. So in unit testing, we test each individual function before testing the program as a whole. So in fact, we can demonstrate this with our rock, paper, scissors code. So let's do a bit of unit testing here. So instead of running all of our functions, so instead of running the entire game, let's just add some testing code. So I'll create another testing function. Say def testing. I'm going to use a new keyword here. This is assert. So the assert statement is a way of effectively telling Python, if this is true, then do nothing. If this isn't true, then crash the program. So it's a way of making sure that your code can't get past this point without certain conditions being met. So it's also a good way of testing. So if any of these tests don't work, then this testing function will fail. So I can say, for example, assert that game results for rock and rock. So if it's a tie, then we'll assert that equals 0. We can assert the game results for, use the example that we just had, paper and scissors. So that's if the user throws paper and the CPU throws scissors, then that should be a -1. And you can continue on testing all these different types as you would. Make sure we run this code, so we'll say testing, and then try this out. So notice this isn't going to test the entire game, it's just going to run the game results function with controlled inputs so we can verify that it's giving us our expected outputs. Save and run our code, we'll say python rps.py still, and here it says it's a tie and you win. And then we got an assertion error. Did I put this one backwards? Ah, yes, I did. The game results go CPU and then user, which perhaps I should have described a bit better. So in this case, I guess we get to see what an assertion error actually looks like because I wrote it backwards. So if our assertion's wrong or if our code is wrong, then we get what's known as an assertion error. So assertion error is just Python crashing the code because of the thing we told it to do. So it says, because this statement isn't true, then it's an assertion error. So if we want to fix this one, in this case, we would put it in the correct order, save and run. And now it just runs to completion. So it's a tie, you lose. We could do one where it's flipped. Assert game results And in this case, you should test all 9 different combinations, and then you have this testing function available. Anytime you change the game results function, you can test it again. So this is the idea behind unit testing. We have these individual tests checking out all of our functions. We should do similar operations for get the CPU throw and for get user input, but the assertions would be a little bit different because in this case we have some random operations happening in both of those. With user input, it's whatever we type, and with CPU throw, it's just a random number, so it's going to be different every time. So we couldn't just use straight equality to determine the outcome of those. We'd have to have a much more complicated expression, like is it one of these values? Another form of testing is what's known as regression testing. And this is similar to unit testing in that we're still attempting to verify our code to find that it's giving us the expected outputs, and it's running to completion, it has no errors. The idea behind regression testing is after we've made changes to our code, so all the debugging that we just did, we want to run our code again to make sure that the changes we made didn't introduce any new bugs. For example, this could mean playing the game many more times or running through our unit tests a second time. All right, and that is it for the chapter on debugging. We've covered a broad scope introduction on all things debugging in Python. We saw the general process and the mental attributes that go into debugging things effectively. We saw the 3 main types of errors, so syntax errors, runtime errors, and logic errors. We also saw how to generally debug these things. We saw how to do that using basic tools like print statements, and we saw how to do that with more advanced tools like the IDE's debugging support. That's it for this video. I'll see you in the next one.